Okay, our first speaker is Daine Danielson, who will talk about black holes are watching you.
Yeah, so I'm Daine Danielson. I'm going to tell you about some work done at the University of Chicago, along with Gautam Satishchandran here, who will give the next talk, and Bob Wald. And I'm just going to tell you about a spooky fact that black holes are watching you. And you can read about it in this series of papers here, including this Gravity Research Foundation award-winning essay, which is a pretty brief summary of what you'll hear here. So black holes are well known to be destroyers of quantum coherence. And the purpose of this talk is to show them to be even more insidious destroyers of quantum coherence than has previously been known. And to make the point, to illustrate it, I'm going to use a Gautam experiment. So here I've drawn Alice, an experimenter coming in and using a Stern-Gerlach apparatus to carefully create a quantum spatial superposition of a massive or charged body. And after some time t, Alice would like to check that her quantum superposition has remained quantum coherent. And to check this, she's going to recombine her superposition with a reversing Stern-Gerlach apparatus and look for signs of quantum interference. Now, in flat space-time, Alice can always maintain coherence. Well, she can maintain coherence only if she avoids emitting entangling radiation to infinity. I'm assuming the environment is well under control here, but she better not move her particle together so quickly that it radiates to infinity. And she, of course, conversely, can avoid producing such radiation if she performs her experiment sufficiently gradually that she doesn't emit a lot of radiation. Now, okay, that sounds good. Now suppose that Alice is performing her experiment in a stationary laboratory outside of a black hole, which I've depicted over here. You might ask, why should this be any different than the story in flat space-time? So to illustrate why you might expect it to be different, let's extend the Gautam experiment a little bit. So we have Alice performing the same experiment, but now behind the event horizon of the black hole, suppose there is another experimenter, Bob. And Bob, well, he's hiding there, could attempt to measure Alice's static superposed gravitational field, which extends into the interior of the black hole, as I've illustrated here. So he's sitting in this static field, he's going to measure it. He could choose, for instance, to release a particle from a trap and see which path it takes. The particle's trajectory will become entangled with the gravitational field, and therefore which path Alice's particle took. But of course, Bob can choose to perform a measurement or not perform a measurement. And if his particle becomes entangled with Alice's system, then of course Alice's system is decohered. But unlike a Bell pair, Alice can tell by her interference experiment whether or not she's been decohered. So this is paradoxical, because it seems as if Bob might be able to signal from Alice from within the black hole by choosing whether to affect her quantum coherence by performing a measurement or not. So this should seem paradoxical. Don't worry, physics isn't going to fall apart. This gets resolved, but it should be puzzling how this works. Now, there is one way out. One possible out for this is there wouldn't be a paradox if, for some reason, Alice was always decohered outside the black hole by an amount consistent with any possible hypothetical Bobs that might or might not be doing measurements behind the event horizon. And then she'd learn nothing based on her decoherence. That wouldn't teach her anything about what's going on inside, because she's always decohered to some degree. And it raises the question, do black holes always decohere superpositions in their exteriors? So let's find out. Let's see. So to answer this question, we have to ask, when can Alice maintain quantum coherence? Assuming, again, environmental factors are kept under control. So from here on out, I'm going to consider an electromagnetically charged particle, because the analysis is a lot simpler, and the moral of the story is exactly the same. So her particle carries a charge Q, superpositions of a size d, and to maintain coherence, Alice has to just ensure the number of entangling photons she produces in the process of her experiment is much, much less than 1. If Alice recombines sufficiently gradually, as I said before, but now quantitatively, if her time is much larger than the effective dipole of her superposition, then if she were in flat spacetime, as we said, she would avoid radiating any entangling photons, and she wouldn't decohere. This avoidance of radiating entangling photons becomes impossible in the presence of a black hole. And that's what we're going to see. So, of course, just as in flat spacetime, if Alice performs her experiment sufficiently gradually, she will indeed prevent radiation from escaping off to infinity. That's the same. But radiation can also propagate through the event horizon in a black hole spacetime. And we're going to analyze that radiation and find a different story. So, let's consider just the electromagnetic field on the event horizon sourced by one branch of Alice's experiment. Maxwell's equations take a nice, simple form, where in this equation, this is telling us V is affine time along the horizon, and these capital A indices are angular indices transverse to the horizon, and or tangent to the horizon, going transversely. Evolving Coulomb field on the horizon gives rise to radiation falling into the black hole. That's what this equation says. And of course, the electric field is nothing but the time derivative of the potential. So as Alice's Coulomb field changes, a delta in the Coulomb field, because she's displaced her particle, that registers on the horizon as a change of the Coulomb field, which when you integrate gives rise to a step function-like change in the vector potential that registers on the event horizon. That's what I've illustrated here. That's just the angular components of the potential pulled back to the event horizon. And you can see Alice's experiment as the particle is originally at some radius b, it gets displaced, you get a new value, and then it comes back over some time delta v. And for large delta v, because of this step function or bump-like behavior, you get a 1 over omega behavior in the Fourier transform of the potential, which says that this is peaked at very low energies. But if you calculate the number of photons in this field excitation, it grows logarithmically in delta v, which for large delta v could become large. So there's a lot of photons, even though they're soft. Of course, in her proper time, that logarithmic growth in delta v becomes a linear growth in time. So the difference between the branches of her experiment is going to source a number of entangling soft photons that's growing linearly in her lab time, just by displacing her particle. And for a long time, of course, this will be bigger than 1, and she's going to be decohered no matter what else she does. And note, for instance, a star or some other horizonless object would not give rise to this effect. So let's plug in some numbers and see how big the effect is. If Alice's superposition, the superposition coherence time will scale like this. So if our sun were a black hole, electron superposed by a meter here on Earth would decohere in, drum roll, 10 to the 32 times the age of the universe. Okay, that just doesn't sound so exciting, but if the experiment were done at the innermost stable orbit of the black hole, that same electron would decohere in 5 minutes. And of course, the analysis I've done is for E and M, but same analysis, more or less, goes through for linearized quantum gravity for any massive particle. And all objects source gravity. So any superposed body whatsoever will decohere in the presence of a black hole. And that effect scales like this. And I won't even bother telling you how weak it is. It's insanely weak. But it is universal, which is somewhat interesting from a fundamental point of view. So black holes harvest information about quantum superpositions outside their horizons by means of long-range fields sourced by the superposed matter. This exerts a fundamental rate of decoherence, and eventually, a black hole will decohere any superposition in its exterior. So that's the end of this talk. But next, Gautam, my co-author, is going to explain the effect in much more detail and also show that it arises in much greater generality than I've discussed here. So, thanks.
Maybe this will be discussed in the more general case. Is this exclusive to event horizons, or is it going to occur in the parent horizon, for example?
It occurs whenever you have a killing horizon, actually. That's what Gautam will tell you.
Yeah, you've assumed that black holes are eternal and integrated to infinity, but if we ignore the environment, they'll evaporate.
Yes, absolutely.
So does that remove this effect or not?
No, it doesn't. The effect for reasonable parameter ranges, the black hole, reasonably sized black hole, matter reasonably close to the black hole, the matter will decohere long before the black hole is evaporated, and the calculation is done in such a way that it doesn't depend in any way whatsoever on the long-term fate of the black hole.
We're going to thank the speaker again. The next speaker is Gautam. Please get on the microphone. Satishchandran, who will continue talking about horizons are watching.
Okay, so I won't have to go through any of this in any detail. And while Daine just gave a really nice introduction to what I'll be talking about, and well, you might wonder what else I have to say on the subject. And well, let me just recap what Daine just showed. Daine was showing you that if you take a quantum superposition in the presence of a black hole, these long-range fields which register on the horizon of the black hole result in this constant rate of decoherence of the superposition via this entangling irradiation that must be emitted into the black hole. Not to infinity, no matter how slowly you recombine. So you may, the question period certainly started off with some questions, and some of these were asked. And so you might have some questions, like, well, what about other horizons? I won't have time in this talk to talk about cosmological horizons, but hopefully I presented in such a way that you could extrapolate in your own minds how the calculation would go. I'll go over the Rindler horizon in some detail. As was just discussed, black holes radiate, horizons radiate. What about the decoherence due to thermal radiation that's present in Alice's lab? And Daine alluded to a story about Bob's, inside the black hole. This Bob is not Bob Wald. It's a skilled experimentalist. And you might wonder, well, what is that story? Is that really a precise statement? So if you fall asleep in this next 10 minutes, the statement is that killing horizons, any killing horizon, obtains which path information of quantum superpositions in their exterior. The effect is distinct and much larger than the decoherence due to the thermal radiation present from the horizon. And the decoherence is equivalent to the optimal which path information obtained by any number of Bobs in the interior of the horizon, on the other side of the horizon. Okay? So I hopefully can get through all of that in this short talk, but let me just start with the Rindler case. The Rindler case is very nice because you can just validate all of these calculations. You might be worried quantum fields in curved space-time, very difficult to maybe calculate things. This is a very nice example where you just have Alice's lab constantly accelerating in flat space-time, and as we all learned in elementary school, that you get a Rindler horizon at t minus c equals 0 at this surface here. And this is Alice separating and recombining the particle. Maybe this diagram is a little nicer, matches to what Daine showed before, where now I have a Rindler, this planar horizon here, and Alice is maintaining some constant distance from the horizon and doing this separation and recombination. Okay, and what's the story? Well, the equations, Maxwell's equations, and everything that Daine was just saying exactly go through, where now the Coulomb field registered on the horizon is the orthogonal component of the electric field. These tangential indices are now indices tangential to the planar surface, and this is divergence on the plane. And this change in the Coulomb field on the horizon will generate soft photons, Rindler photons, through the horizon. This change in the Coulomb field will give rise to this change in the potential between early and late times when I displace the particle. And if I suffer this change in the potential, if I then calculate what the number of photons are produced due to creating this change in the potential, I get a constant production of soft photons through the horizon of the black hole. This should be almost exactly the same. I just took Daine's slide and replaced some indices. Okay? So it's not important that you remember the formulas for how quickly Alice decoheres in the presence of such a horizon. The key thing is that it's due to very, very soft photons, so photons of 1 over affine time, so exponentially suppressed at killing time. And you can work out exactly how quickly Alice decoheres due to her proper acceleration of her lab. Okay, so this is all on the Rindler horizon. We didn't learn quantum field theory on Rindler horizons. We learned quantum field theory with, from the inertial perspective. And you can just validate all of these things from the inertial perspective. It's with a lot more effort. You can calculate the number of photons that Alice emits out to null infinity. And after you do quite a long calculation, you find exactly the same agreement. You get these number of entangling photons growing linearly in the time that Alice maintains the superposition. But now the inertial observer is blue shifted relative to this accelerating charge. And so he sees blue shifted radiation. He sees high frequency radiation, as opposed to Alice, who thinks she's emitting low frequency. Okay? So what about thermal radiation now? Well, horizons famously radiate. And is this effect simply due to collisions with the thermal bath of photons that are present in her lab? Well, you can calculate. Well, this is the decoherence time that I gave you for our effect. You can calculate the decoherence time due to collisions with the thermal bath. The first thing you should note is that these are different formulas. Okay? And one depends on the mass because you're colliding with the thermal bath, and the other one obviously doesn't. And not only that, you can straightforwardly show, and it should be intuitive, if the wavelength of the thermal photons are not as big as the size of my superposition, they'll be very inefficient at decohering my superposition. So in the black hole case, I don't want Alice to make a superposition of order the size of the black hole. Okay? And in general, the decoherence rate due to the emission of soft gravitons and photons through any killing horizon is always much larger than due to the decoherence rate due to thermal radiation. So you can safely neglect this effect, and it's fully a distinct effect due to the presence of the horizon. Okay. And the last thing I want to mention is now more recent work that will be out fairly soon, which is what is the story from the other perspective? So Daine gave you this intuition that black holes, the decoherence due to black holes, should be thought of in some sense as, or you can conclude it from the fact that you could put bobs on the other side, right? Again, expendable bobs, not. And so anyway, so let's say take some bounded region B inside the black hole, and if we take what is Bob measuring? Well, he's measuring whether or not Alice went right or left, the long-range Coulomb field, psi1 if Alice went left, and psi2 if Alice's particle went right. And we want to try to have Bob measure whether or not Alice went left or right. So this is the picture I want you to have. I'm letting Bob have some access to the interior of some subregion of the black hole in this bounded region, and he's doing this measurement. This is probably not the best measurement. You should probably have some joint measurement of many possible Bobs falling into the black hole. Again, I'm just going to keep throwing them in and have them measure as good as they possibly can. Okay? And this, you can borrow a very nice tool from quantum information, which is the fidelity. So the decoherence due to the optimal Witch path measurement, we're trying to distinguish two possible quantum states in any bounded region of the space-time, is measured by this quantity called the fidelity. I won't give you a formula because I have such little time, but the error in Bob's optimal measurement to distinguish two possible states in one region is it's this number, which is f, which eats two of these states, and it's 1 if he can't distinguish it. It's 0 if he's perfectly able to distinguish it. Okay? And in quantum mechanics, the fidelity is just the trace of the density matrices of psi1 and psi2. But in QFT, density matrices famously are undefined in local regions. You have to use some fancy machinery, but effectively this is what he's doing. So it's a measure of how good the optimal Witch path measurement can obtain trying to distinguish psi1 and psi2. Okay, yeah, so I'm nearly done. So what can you prove? Well, you can rigorously prove the following 3 statements. Well, one is the fidelity is strictly a decreasing function of t. What does that mean? That means that as I increase this region, Bob is truly getting the best possible measurement that Bob can make. He's truly distinguishing better and better which direction that Alice went on. Not only is it decreasing function of t, you can connect it to what Daine was saying before. The best, the distinguishability of these states is really directly bounded by the number of soft photons that Alice has emitted throughout just holding the superposition in the exterior of the black hole. And not only is that the case, but in the most interesting statement is that in the limit as t goes to infinity, so now I'm letting Bob or some collection of Bobs have access to the entire interior of the black hole, do the best possible measurement that they can possibly do, you recover exactly the decoherence that Daine calculated in his talk. So what is the punchline? And it's completely cut off. So the decoherence due to the black hole or any horizon is actually mathematically equivalent to the optimal Witch path measurement made in the other side of the horizon by any collection of joint measurements of any Bob. Okay, so since I'm running into my question period, and I'm sure you guys do have some questions, let me just end with this. Well, I think the fact that black holes or cosmological horizons and horizons in general really do eventually, in this precise sense, decohere quantum superpositions in their exterior or vicinity should be or is of fundamental significance to our understanding of the nature of such structures in a quantum theory of gravity. And let me end there. Yeah, so it turns out, well, the decoherence rate is slow enough that she can just like the compact object will be in her past causal diamond, like the surface of that star. So in the sense, there is no, like she could do better measurements of obtaining whether or not there's a compact object there.
There is time for her to send a probe. Right?
Yes.
Does she need to? Could she just figure out that it's a black hole versus not a black hole just by measuring?
Yes. Yes, there's a caveat as to whether or not the star has been eternal or it was formed by some collapse of something. Basically, the blue shift outside the star, like how long does it take for the quantum state in the exterior to really settle down to a stationary state, is the key time scale. So for an eternal star, for a star that's formed that is like of order, the size of the star is of order 3m or something like that, or 5m or whatever. I don't know what, I'm not an astrophysicist, so I'm just going to make a bigger number than the horizon. Of those timescales, that blue shift timescale is very small, or is negligible, so the point is that the quantum state settles down almost immediately, and she could make this distinguishing measurement. For the fuzzball case or something like that, where it's epsilon away, the quantum state settling down to true vacuum, which is the exterior of the star, is very long. So then it would, she would have to wait a long time to be able to determine this effect. That's consistent with what I said before. Hopefully that answered your question.
Let's thank the speaker again.